In this lesson, we're going to be looking at collisions in two dimensions. So in previous lessons and videos, we looked at collisions in one dimension, but most collisions are actually done in three dimensions. Well, three dimensions is beyond the scope of this course. For this course, we only have to look at a max of two dimensions. So things are colliding all the time. So we have comets, asteroids, meteoroids collide with celestial bodies in space. We have molecules and atoms constantly colliding during chemical reactions throughout the universe. For instance, in stars, in Earth's atmospheres, and even within our very own bodies. So we have already done collisions that are in a straight line, one-dimensional. Now, in this video, we're going to try and figure out how to do these collisions in two dimensions. Well, in order to do this, we're going to have to go back and use the skill sets that we learned in Physics 20 to help us solve questions that involve two-dimensional collisions. So how do we solve two-dimensional collisions? Well, basically, what you have to do is in two-dimensional collisions, where no external net force acts on the system, the momentum of the system in both the x and y directions remain constant. So, in other words, the momentum of the x in the initial must be equal to the momentum of the x in the final. The momentum of the y in the initial must be equal to the momentum of the y in the final, where the F net is our whole system. So this sounds pretty confusing, doesn't it? So another way of looking at it is just basically this way. We have to separate now everything into their x components and everything into their y components. And we're going to follow our conservation of momentum in the x, and then we're going to follow the conservation momentum in the y, and then combine them back together, just like we did with a whole bunch of calculations in Physics 20. So in our first example, we're going to be looking at two-dimensional collisions in sports. More precisely, we're going to be looking at curling. Sports such as pool, curling, shuffleboard, athletes must really understand how objects collide in two dimensions. For instance, in curling, what you must do is a lot of times you want to have your rock collide with another rock and then curl around or refract or rebound in a way that it's protected from other rocks and moving the rock you hit out of the way or as a guard for you. So let's take a look at our first example, which has to deal with curling. So in this one right here, we have a 19.6 kilogram curling stone moving at 1.2 meters per second north, strikes another identical curling stone off center. And it moves off with a velocity of 1.17 meters per second at 12 degrees east of north. What will be the velocity of the second stone that it hits after the collision? So for this, like normal, we're going to be ignoring friction and rotational effects. So let's take a look at my before pick. It looks something like this. So I have a rock going north and it hits my rock B there. Now my after pick looks like this. So after the collision, rock B moves this way and rock A is going to be moving at 12 degrees east of north. Now using the same concepts as in Math 20, I'm going to switch my angle here. So I'm going to look coming off the east and say this is 78 degrees for my calculations. That way I could use circumference to help me with my calculations. Now the first step we must do here is break everything into their x and y components. So now we're going to look at the conservation momentum in the x and the conservation momentum in the y. So while looking at the x, we know my initial momentum in the x is going to be equal to my final momentum in the x. And if we look at this picture here, I have two stones. I have stone A and stone B. So we have to know the momentum of stone A and B in the initial must be equal to the momentum of stone A and B in the final. Now looking at this, I look at it in my initial, there is absolutely no x vectors. My velocity in the x is, my momentum in the x is 0. So I could cancel off both of my initial because it's going to be equal to 0. So we could rearrange this so I have my momentum of one is equal to the negative momentum of the other. So now we're going to put in our momentum formulas. So mass times velocity is equal to momentum for each momentum. Now looking at this, my masses are the same, so my masses are going to cancel off. So we're just looking at my velocities. And we want to find the velocity of block B and the final of it. So let's plug in what we know for block A. Since we're using Sir-Coxeter-Tix, I know it's going to be 1.17, and we're going to find the x, which is cos, so that's cos 78 degrees. Which gives me 0.24 meters per second west. So now that we are done with everything in the x and my x components, let's take a look at my y components. So once again, I look at this whole system of my initial momentum in the y before the collision must be the same as my whole system of momentum in the y after the collision. Now, in the y before, we have two rocks that have possible momentum. And in the after, my final, I have two rocks with possible momentum. So let's put in the momentum for both of those rocks. Now, we look at this here. I have in my initial only one without a y, and that is my rock B. So rock B does not have an initial velocity or momentum in the y. So now let's substitute in my formula for momentum for each situation. Okay, so which are we trying to isolate here for? We're trying to find the final velocity of rock B. So now I'm going to isolate for that velocity. But before I do that, I notice that each term has a mass which is identical. So I could factor out those masses and divide everything by the mass. So now, let's isolate for my final velocity of rock B. So in this case, we're going to use our substitution now, which is, we have 1.2 meters per second minus, and we're using our Sir-Coxeter-Tix, that's why I always came off the x, minus, we're going to have 1.17, and we're looking at the y, so that's going to be sine 78 degrees. Which is going to give me a total of 0.056 meters per second up. So now let's quickly make a drawing of what we have. So I have a vector going west at 0.24, and I have a little bit going up at 0.056. So my resultant is going to be something like this. So we have to calculate that resultant to give me my answer. So to find my resultant, I have to combine my x and y with Pythagorean theorem and then using tangent. So let's first find my resultant. So we know r squared is equal to x squared plus y squared. We want to isolate for r, so we're just going to square root everything. So let's substitute everything in, which gives me the square root of 0.24 squared plus 0.056 squared. And that will end up giving me a velocity of 0.25 meters per second for my resultant. Now I must find my angle. So I'm going to use tan for Sir-Coxeter-Tix, and tan is y over x. So then again, we're going to get tan, and that's going to be 0.056 divided by 0.24, which will end up giving me 12.9 degrees. Now we found this angle here, so that's going to be north of west. And that gives us our answer. So here are two questions for you to try. I would like you then to pause the video and attempt these two questions. So here is the solution for these questions. So let's take a look at my second example. In my second example, we're having a perpendicular collision. And in this one also, we're going to have coupling. So let's look at my question. We have a 90 kilogram quarterback moving at 7 meters per second at 270 degrees, which is south, is tackled by a 110 kilogram linebacker running at 8 meters per second, moving at 0 degrees, which is going to be to the east. What will be the velocity of the center of mass of the combination? So combination means they're coupling together of the two players immediately after impact. So the first thing I want to do is have a picture and draw a picture to understand. So here's my before pic, where I have the one guy about to hit the other guy. And then I have my after pic, where they couple, and we're trying to figure out what is the velocity in the after pic. Since we're looking at two-dimension collision, once again, the first thing I must do is break everything down into its x vectors and into the y vectors. Now, we're still going to have to follow, like always, the conservation of momentum. So if we're looking at my x, my total initial momentum must be the same as my total final momentum. So my momentum before contact must be the same as my momentum after contact. Now, I look at this for my initial or before contact, I have a linebacker and quarterback. In my final, all that I have is one thing: the linebacker and quarterback are coupled together, so they're joined together. They count as one object. Now, looking at this, in the x direction, my quarterback actually doesn't have a momentum. He only has a y direction. So for my initial, I could cancel off my quarterback initial since it's going to be 0. So now let's plug in my formula for momentum, which is mass times volume. So I'm going to have the mass of my linebacker multiplied by the volume of my linebacker initially is going to be equal to the mass of the quarterback plus the linebacker multiplied by whatever their final velocity is. So now I must isolate for my final velocity in the x. And I'll find out that my final velocity is equal to my mass of the linebacker multiplied by the initial velocity of the linebacker divided by the mass of the quarterback and linebacker combined. And when I substitute that in, I'm going to end up getting 110 kilograms multiplied by 8 meters per second divided by 200 kilograms, which will end up giving me a total of 4 meters per second. So now that we are done with my x components, let's take a look at my components in the y. Once again, we must use our conservation momentum. So my total initial momentum of my two objects must equal to their combined momentum in my final. And just like in my x, I have two people here where we have to look at the momentum for, the linebacker and the quarterback, and the sum of their momentum must be equal to their momentum together combined after the collision. So in my scenario, the initial momentum of the linebacker is only in the x. So if the initial momentum of the linebacker is only in the x, he doesn't have a momentum initially in the y. So we can make that equal 0 and cancel this off. Now what we're going to look at here is we're just going to replace my momentum with its formula for momentum. So I'm going to have the mass of the quarterback multiplied by the velocity of the quarterback initially in the y is going to be equal to the mass of the quarterback plus the mass of the linebacker multiplied by the velocity of them both in the final after the collision. And now what I'm trying to do is I'm trying to isolate for VF. So I'm going to once again isolate for my final velocity of the two collided together. So that's going to end up getting my final velocity is equal to my mass of the quarterback multiplied by the velocity of the quarterback initially divided by the combined mass of my quarterback and linebacker. And now I'm just going to substitute in everything I know, my variables. So the quarterback is 90 kilograms and he's moving at negative 7 meters per second. Because remember, it's going south. And we're going to divide that by 200 kilograms. And that's going to give me a total of 3.15 meters per second south. So now that I have this part here, we can combine both my x and my y vectors to make my resultant. So let's make a diagram to see what's happening. So my x is 4.4 and it's positive, so I'm going to be going to the right. My y is a negative, so it's going down at 3.15. So I want to figure out what is my resultant here. So to do this, I'm going to look at, and we're going to have r squared is equal to x squared plus y squared. And we want to isolate for r, so I'm just going to square root everything. And when I do that calculation, I'm going to end up getting a total of 5.4 meters per second. So now we're going to have to use tan to figure out this angle here. So we're going to be using ticks. So I'm going to have tan 3.15 divided by 4.4. And that's going to give me a total of 35.6. Now, the trick here is if we look up here, we have to figure out, we know this angle here is 35.6. And we want to figure out this whole angle all the way around, so I'm going to have to go 360 minus 35.6. So 360 minus 35.6 will give me a total of 324.4. So my answer is going to be 5.4 meters per second, and it's going to be at an angle of 324 degrees. Here are two more collision questions in two dimensions where two objects stick together for you to try and see if you understood what we did. So pause the video and try these questions. Here are the solutions or the answers to these two questions. So now let's take a look at our last type of two-dimensional collision questions. Well, it's not really a collision. This one is explosion. So we're looking at momentums after explosions. So when we looked at one dimension, this is very similar to the one-dimension recoil questions, because in these cases, my initial momentum is going to be 0. So that must mean my sum of all of the pieces in my final momentum must be equal to 0 as well. So let's take a look at our first question here. We have a 0.60 kilogram fireworks bundle is at rest just before it explodes into 3 fragments. A 0.2 fragment A flies at 14 meters per second west, and a 0.18 kilogram fragment B moves at 19.2 meters per second south. What is the velocity of the third fragment just after the explosion? So here we're going to assume that no mass is lost or anything like that. All the fragments are staying the same. So let's take a look here. Here is my initial thing that's happening. There's nothing. Everything's at rest. So that's before the explosion. My after the explosion, I have a few things that are happening here. I have one rock moving west and one rock moving south. Now, a key thing to remember is both of these velocities are negative, because west is negative and south is negative. And then my third velocity is going to be at an angle. So once again, what I must do is, to solve this question, I always have to break everything in x and y. But before we do that, I have another problem. I only know the mass of A and B. I don't know the mass of C. Well, that's pretty easy to tell, since we know the mass of the total is A plus B plus C together, so then my mass of C must be the mass of total, subtract the masses of A and B, which ends up giving me 0.22 kilograms. So now let's break everything down into their x and y components for momentum. My initial momentum must equal my final momentum, because conservation momentum, it always applies in elastic and inelastic equations. But now here we know my initial momentum is 0. That means the sum of my final momentum must be 0. So I could now write that the momentum of piece A and fragment B and the momentum of fragment C must equal to 0. This could allow us to then rearrange this formula to find the momentum of C. But before we do that, let's look at one other aspect here. We're looking at in the x. So my momentum of fragment B is 0 in the x. So I could just cancel off that momentum of fragment B. And then we could rearrange now for fragment C. So fragment C is the momentum of fragment C is going to be equal to the negative momentum of fragment A. So now we're going to put in the formulas for momentum for both fragment C and fragment A. And now we're going to isolate for the velocity of fragment C. So we have the velocity of C is equal to the mass of fragment A multiplied by the velocity of fragment A divided by the mass of fragment C. Now, all we have to do is substitute in our values for each variable. So one thing that's key that you always have to remember is put the negative in for the velocity, since it's a negative value and it's going west. And then what we're going to end up getting is 13.27 meters per second east. So now that I know my x velocity of fragment C, I can start looking at my y velocity of fragment C. So let's look at my y components. We're going to do the same thing again. So I know my initial momentum of my y must equal to the final momentum of my y. Now the next part is, we know the initial momentum is 0, so the sum of my final momentums must be 0 as well. Except in this case, we have fragment A, which doesn't have any y value. So in this case, we're only going to be looking at fragment B and fragment C, where we'll say the momentum of fragment C is equal to the negative momentum of fragment B. So now we're just going to substitute in my formulas for momentum of B and for the momentum of C. So I'm going to have the mass of fragment B multiplied by the velocity of fragment B is equal to the mass of fragment C multiplied by the velocity of fragment C. And I want to isolate for the velocity of fragment C. So that's going to give me the velocity of fragment C is equal to the mass of fragment B multiplied the velocity of fragment B divided by the mass of fragment C. And remember, that is all negative. Now, I am going to do my substitution. So I'm going to end up getting 0.18 kilograms multiplied by negative 19.2 meters per second, because remember, it is going south, all divided by 0.22 kilograms. What will that give me? That ends up giving me 15.7 meters per second. And that's going to be a positive because we have two negatives that cancel each other out. So now that I know my x and y vectors, let's try and figure out my resultant. But first we need to draw a diagram to help us understand what's happening. So we first go east at 13.27. Then we end up going north at 15.7. We want to find the resultant, which will be over here. So then I'm going to use the Pythagorean theorem to try and solve for my resultant r. So we know that r squared is equal to x squared plus y squared. I'm going to simplify this, so then I end up getting the square root of 13.27, which is my x, plus 15.7 squared, will give me a total of 20.6 meters per second. Then I'm going to have to take my tan of my y divided by my x, so the inverse of tan of y divided by x, to figure out my angle. And my angle I end up getting is 50 degrees, which gives me a total of 20.67 meters per second at 50 degrees north of east, since we're trying to find this angle right here. So here are two explosion 2D dimension questions for you to tackle by yourselves using the method that you just learned in the previous question. So I want you to pause the video and try these two questions. The answer to these questions are this right here.